Right, welcome back to our lecture 6 videos on the application examples, and more specifically the cart rolling on a flat surface example that we want to look at. We're applying this via Nikravesh's body coordinate simulation program, the DAP-BC workbench. So in the previous part, we've looked at cart A, and we said over there we can actually go and define the driver motor as a driver constraint function using the type A function. For cart B, we're actually going to consider the type C function in this case. So the model itself is the same as what we had for cart A, except for the driver function referring now to a function C instead of function A. To perhaps better illustrate this, we can consider the DAP type C function and the input arguments that we need to give it. So the first derivative of this function rises from 0 to a final value during a specified time period and keeps that value for the remaining duration of the simulation. And this is now inherently different to what we had for cart A. In that case, once we did initial condition correction, we actually saw that it remains at a constant angular velocity of minus 2 pi radians per second. In this case, we actually want to see some sort of a ramp up in our angular velocity, so we expect it to start from 0 and then go to minus 2 pi radians per second. So there is some acceleration component playing a role over here as well. Now this function can be useful in simulations where a driver should raise the velocity or the first derivative from 0 to a specified speed. The general expression for this function is given as f, which is a function of t, equal to, and then we have an expression over here which contains 4 different coefficients that need to be calculated. So this function and its derivatives are depicted in figure B8. If we look at our function itself, we know that it starts at some value f start, and then it raises the value up to a final value which we can call f end at t end, and we also start over here at t start, so our starting time. Then for the second derivative, or the first derivative rather, we once again consider t start, and over here we want the first derivative to be 0. Then we have the df dt curve, which then goes up to df dt max, and this is then at t end. If we consider the third graph over here, or the second derivative, then both at both t start and t end, d square f over dt square needs to be equal to 0. And for our final third derivative, we once again want t start and t end to have 0 values for d3f over dt3. And these are now the properties that we want to apply in order to construct this type of function. So the function has a 0 first, second, and third derivatives at the start, and then also a 0, second, and third derivatives at the end. So we can see the second and the third derivatives are 0, but the first, second, and the third derivatives are 0 at the start. The first derivative also has a non-zero value at the endpoint. So based on all of this, the user must supply 4 parameters: the start and end values for the time t, so t start and t end, the start value for f, which is f start, and then also the end value for the first derivative, so df dt max, which is also equal to df dt end, so this value over here that we see. The program DAP will then compute the 4 coefficients of equation 8.3, and then it will apply it as a driver motor function to whatever motor we are applying to the system. Right, so for cart B, the angular velocity of body 2 needs to start from 0 and reach the desired speed of minus 2 pi radians per second in 2 seconds. So they basically give us all of the information that we need to give as an input to this function. Hence, we need to specify the 4 parameters as follows. T start is equal to 0. So if we don't specify it, the system is in any case going to assign the default value of 0. T end we know is 2, and this might actually differ from the final time that we specify when we actually run the DAP BC simulation. So if t end is 2 seconds and we specify our final time to be 3 seconds, what the system will actually do is once it reaches on dfdt, once it reaches dfdt max, it will then remain constant at that value for the remainder of the time interval. Right, then f start is also equal to 0, so also the default value. And then dfdt end is equal to minus 2 pi. And this is simply based on the angular velocity that we want to reach at the end. The program DAP will then compute the four coefficients, and the first derivative of the function c will then look as shown in figure 8.10. So this figure that we have over here, which indeed starts at 0 and then ends at minus 2 pi radians per second. This is simply shown as minus 6.28 on this graph. Okay, so moving on to exercise 8.8, the first task that we have to undertake is to review the input files for this model. And then we want to execute DAP and then execute anim and observe the actual animation of the response. So if I go over here, what I'm first just going to do is clear all, close all, so that I'm working with a blank workspace. And then I just have to open the files for card B. So this will be in animate, in bodies, in forces, the functions, joints, points, and any U vectors that I want to specify. Okay, so considering in animate, this more or less remained the same as what we had for card A. So we still have 2 points, points 5 and 6, that we want to use just for animation purposes to see how these wheels are turning. Then we also have a rectangular shape that we assign to body 1, so the main body of the system, and then 2 circular bodies to denote the 2 wheels as well. Then for x min and x max, we've chosen 0 and 4. We can actually make this a bit smaller, so let's perhaps make this 2.5, and it's easy for me to change it because I've done the animation previously and I saw that if we make it any smaller than 2.5, then it's not going to show the entire animation. But in your case, you would probably perform a preliminary animation. Once that is done, you can determine whether your bounds are large enough to accommodate the motion of the system. In my case, I'm just going to leave it at 2.5 for now. Then for in bodies, this also remained the same as what we had for card A. So we once again have 3 bodies, a main body, and then the 2 wheels as well. In forces, we simply have the weight acting on the system. Then for in funct, and this is now where we changed our function, we're now using a type C function. And the only 2 things that I specified for this one is t end, which is 2 seconds, and then dfdt end, which is minus 2 pi radians per second. The fact that I didn't specify t start or f start means that it's automatically set equal to 0, and that is indeed what I want for this simulation. Then in joints also remain the same. We once again have the relative rotation driver at the end, so nothing really changed over here. The function itself changed, but the function index still remains 1, since we only have one function in our list over here that we use. Then in points still consists of 4 points that we use to connect the revolute joints to the system, or to connect the main body to the 2 wheels. So that is what these points are used for. And finally, in U vectors is simply an empty list, since we don't have any translational joints that we specify over here. Okay, so with that now done, it says that we need to execute DAP and then execute anim and observe the animation of the response. So if I do that, I'm just going to type in DAP card underscore B, and then yes, I want to correct the initial conditions, and what I now notice is that x dot, y dot, and phi dot are all equal to 0, and that is indeed what I expect. I do expect some acceleration from 0 radians per second to minus 2 pi radians per second. It is also just important to notice that on this graph, we actually have a higher f start or a starting value for our phi dot than what we have at the end. So this is basically just a reflection about the x-axis of these functions that I have over here, more specifically the second df/dt curve that I have over here. Okay, so that is also supported within this type C function. Okay, and I'm going to run this now for a final time of 3 seconds and a reporting time step of 0.1 seconds. And we can see that it now terminated after 240 function evaluations. So now I'm just going to run anim. And I'm just going to press a key over here, and then we can open it up. And what we expect to see is that for the initial motion of the wheels, it's going to move fairly slowly, and then once it basically reaches the angular velocity of -2 pi radians per second, we expect to see faster motion of the wheels and then of the actual cart itself as well. Okay, so now we can see the motion has terminated, so I'm just going to close over here. Right, and we did indeed see the effect of the angular acceleration on the wheels. Initially we saw small changes in the angle for that line that we drew on the discs, and at the end we saw that as a function of time, those rotation angles changed more and more for each sampling interval where it plotted the animation. Right, so next up we want to execute post, and we want to plot the angular velocity of body 2 versus time. The plot should reveal that the angular velocity has been varied from 0 to the final value in the described time period as depicted in figure 8.10. So to do this, we're just going to run post, and just to iterate what we said in the mind map as well, we expect to see a change in the angular velocity from 0 to -2 pi radians per second after 2 seconds, and then for 2 to 3 seconds we expect to see a constant angular velocity of -2 pi radians per second, or -6.28 radians per second. So if I run post, then I can just go and plot it. So I'm just going to say plot t, and then it's going to be rd all of the times, and this is for body 2. And if I close the brackets, then I can see over here, let me just check, I think I actually plotted rd, so I actually want to plot pd over here. So pd, if we go down, is then the angular velocities, and in this case it's a 31/3 matrix. So 31 is the number of time steps that I have, and 3 is then the number of bodies. So in my case, I'm interested in body 2's simulation or its post-processor results. So I'm just going to plot PD for body 2. And if I plot that, then I can see that indeed it starts at 0, and then after about 2 seconds, it now plateaus to -6.28 radians per second, and then it remains constant up to the end 3 seconds. So that is indeed fine. Right, we now want to plot the torque associated with the prescribed rotation of the rear wheel, so body 2, as well as the reaction forces on the rear driver wheel and the front driven wheel. So let's perhaps first have a look at reaction forces, and this is now referring back to section 4.4.2 in the PMD textbook. And you'll remember that we actually covered these kinematic joints and revolute joints in one of our previous lectures. For review, we're just going to reconsider it over here. So reaction forces or torques act between two bodies along or about the axis for which no relative motion is allowed. A kinematic joint, we know, removes one or more of the three relative degrees of freedom between two planar bodies. And these imposed restrictions on the relative motion expressed analytically are then called constraints. So we can consider the two bodies connected by a pin joint, shown in figure 4.10a, and this is once again something that we considered previously. We know that this double arrow over here indicates relative rotation between the two bodies, and this is now an assembled view. If we disassemble these two bodies, I and j, from one another, we're going to end up with reaction forces in the x and y, or in the 1 and 2 directions. A pin joint allows the bodies to rotate relative to one another, but it eliminates the relative translation between the attachment points along any two orthogonal axes. Since this joint removes two relative translational degrees of freedom, the resultant reaction force on each body can be described with two orthogonal components, lambda 1 and lambda 2. And that is then the reaction forces that we see over here in this figure as well. A circular disc may roll against the flat surface or line of another object, as shown in figure 4.10g. Now in this case, body I and body J are moving. In our case for the cart, we actually consider body J as being ground, so it's stationary while the discs are rotating. So the fact that the two bodies remain in contact means that there is a reaction force lambda 1 perpendicular to the line or the tangent line of contact. And this is basically seen as a normal force acting between the disc and then, in our case, it's ground, or then a second moving body which is in contact with the disc. In addition to this, if no slippage is allowed between the two bodies, another degree of freedom is removed. This condition necessitates a second component of reaction force, lambda 2, that must also be considered. So over here we have lambda 2, which is then enforces the no slip condition. So we expect a disk to also impose two constraints in order to minimize the degrees of freedom, or to remove 2 degrees of freedom. Right, so moving on to section 13.2, and this now deals with the constraint formulation. And we also looked at this previously, but the constraint equations of motion, including all the kinematic constraints, are expressed in equations 1319 to 1322. And to solve equation 1322 for the accelerations, we appended to the acceleration constraints of equation 1321 to form the following set of equations. So we have basically a matrix over here that consists of a mass submatrix, and then we have a Jacobian submatrix and its manipulated version, and then also a zero submatrix over here, which we multiply by a vector consisting of the coordinate accelerations and then also the Lagrange multipliers. And we simply set this equal to any externally applied load vectors, and then also this lambda, which is also a constant that we looked at previously. So section 13.6 then refers to the combined analyses, and assuming that there are n v coordinates and n c independent constraints, then it means that the number of degrees of freedom is simply nv, the number of coordinates, minus the number of independent constraints. The NV equation of motion and NC acceleration constraints based on equation 1323 are then once again given by 1361. So you'll see that it's basically the same as what we had for 1323. So let us assume that we include ND driver constraints, which we can express in this form over here. So superscript dr indicates that we're working with driver constraints, phi, which is a function of q, and we set that equal to a function of t. Then if we derive with respect to time the driver constraint, then we end up with f dot t, which is equal to, once again, the driver Jacobian matrix that we have over here, multiplied by q dot, so our velocity vector. And then if we go one step further and we derive it once again, then we end up with f double dot t, which is equal to, and we simply apply the chain rule over here, is then superscript driver, so the driver Jacobian matrix time derivative multiplied by q dot, which is the velocity vector, plus the driver Jacobian matrix multiplied by q double dot, which is then the acceleration vector. The second time derivative of the driver constraints can then be rearranged in equation 1362 in this form that we have. With the inclusion of these driver constraints, equation 1361 then becomes equation 1363. And what you'll notice, we basically just appended the driver Jacobian matrix to the existing Jacobian, or the existing matrix that we had over here. Isolating the equations of motion from equation 1363 then yields mq double dot, which is then equal to the constraint Jacobian matrix multiplied by lambda, and these are the constraint Lagrange multipliers, plus the driver Jacobian matrix multiplied by the driver Lagrange multipliers, and then any externally applied forces as well. So the one that we are most interested in is this driver Jacobian matrix multiplied by the driver Lagrange multiplier, because these will then yield the driver reaction forces. Okay, so that's just more from a mathematical perspective that we're considering that. Then we want to rather focus on section 7.2.9 and how to construct the system Jacobian for our multibody mechanism. The Jacobian matrix for a multibody system is constructed from the Jacobian submatrices of its joints. So in this subsection, we use a simple example to show the process of constructing the Jacobian matrix in its generic form. So if I expand over here, the example that we want to look at is this generic multibody system consisting of 3 moving bodies. And if we look at the joints that we have 3 pin joints, A, B, and C. And then we also have 1 sliding or translational joint, which acts between bodies 2 and 3. And these then yield 8 algebraic constraints, so 2 per joint. Reason being, a pin joint has 2 reaction forces or 2 independent constraints, and we have 3 pin joints, so it's 2 times 3, which gives us 6. And then our translational joint that we have over here also imposes 2 constraints. So it's 6 plus 2, which then gives us 8 algebraic constraints. So for the moment, let us assume that the ground body 0 is a moving body. Therefore, we have 12 coordinates, so 3 per body. And the system Jacobian matrix should be an 8 by 12 matrix. Okay, we refer to 3 per body since we're working in the x-y direction, and then rotation about the z axis. And since body 0 is now also included, we have 4 bodies, so 4 times 3 is then 12 coordinates. Okay, so the number of rows that we have matches the number of algebraic constraints imposed by the joints, and the number of columns that we have matches the number of coordinates for the bodies. Assume that the joint constraints are assembled in the following order. So we have A, B, T, and C. So we first have pin joints A and B. Then we have the translational joint T, which acts along the longitudinal axis of body 3. And finally, we have pin joint C as well, which is situated over here. So the Jacobian matrix for the pin joint A between bodies 0 and 1 can be obtained as 2 2x3 submatrices from equation 7.17. And this is then this set of equations, or this equation that we have over here. So we specifically look at the revolute joint, which imposes 2 constraints. And we can go and basically reduce these submatrices over here to denote the constraint Jacobian matrix for body I pertaining to revolute joint, which is imposing 2 constraints. And then since it's acting between bodies I and J, I also have to give the Jacobian matrix pertaining to J for the revolute joint. To understand the SIP rotated and minus SJP rotated, we can consider figure 7.3b and then 2.6 as well as equation 2.12. So we first consider equation or figure 7.3b over here. And in this case, whenever we talk about SIP, what we actually refer to is a vector from the center of mass of body I to point P. And then the same for body J. So in that case, it will be a vector from body J center of mass to point P on body J. Now, the rotation of these vectors are discussed at the hand of figure 2.6. So in this case, we have a vector A, and if we break it up into its components, we have A1 and A2, since we're using a 1-2 axis system over here. Now, whenever we rotate this type of vector, we simply rotate it counterclockwise 90 degrees. And then we end up with this A rotated over here. And now we can see that now the X component, or the 1 component, is minus A2, and the 2 component is A1. And equation 2.12 can then be used to express A rotated. Right, so what we are perhaps more interested in is how the interaction between these joints are shown in the Jacobian matrix and how we denote the bodies within the Jacobian matrix as well. So these submatrices denoted by D0A, so this just says the constraint Jacobian matrix for body 0 pertaining to joint A, and D1A, which is then the constraint Jacobian matrix for body 1 pertaining to joint A, occupy the top 2 rows and the left 6 columns of the overall 8x12 Jacobian matrix. And the reason for this is simply because we first have joint A defined. So it's going to occupy the first 2 rows and the first 6 columns of the 8x12 Jacobian matrix. So similar to this, the submatrices for other joints are placed in their corresponding rows and columns to form the following matrix over here. So if we look at this first row over here, we have that joint A acts between bodies 0 and 1. So that's why I denote D0A and D1A. The rest are just zero values. Then in the second row, I have the constraints pertaining to joint B. In this case, joint B acts between bodies 1 and 2, so I group them together. And then the translational joint acts between bodies 2 and 3, and finally I have joint C, which acts between bodies 0 and 3. So you'll notice whenever I set up this type of submatrix, the rows, so if I go from row 1 to row 2, row 3, row 4, then the joint is the one that's changing, so it's A, B, T, C. And then if I move across the columns, so column 1, 2, 3, then it refers to the body that I'm working with, so 0, 1, 2, and 3. Now, it's also important to notice that in this matrix, each generic row represents 2 actual rows. So I'm going to break D0A up into 2 rows. D1B will also be broken up into 2 rows. So at the end, I'm going to have 8 rows. And each generic column represents 3 actual columns. So once again, this column is broken up into 3, this column is broken up into 3, and then I have 3 times 4, which gives me my 12 columns that I expect. The blanks simply represent any 0 entries. And we can note that a sliding joint and a pin joint have the same generic form. So in other words, the same number of constraints are imposed by them, and they have the same number of coordinates expressed across them. So far we have considered body 0 as a moving body in order to make the process of constructing the overall Jacobian matrix more easily understood. However, since body 0 is a non-moving body, in other words, its velocities and accelerations are always 0, we can remove its corresponding columns from the Jacobian matrix. This yields an 8x9 system Jacobian matrix, as shown over here. So what we basically did was to remove this column that we have over here. Okay, so then if the process of constructing the overall Jacobian matrix is well understood, there will be no need to first include the ground as a moving body and then remove its corresponding columns. The Jacobian matrix could be constructed in its final form directly, so that would also be fine. So the combined constraint and driver system Jacobian for our Card B simulation is then given by this matrix that we have over here. And if we consider it, we see we first have our constraint Jacobian at the top, and then we simply append our driver constraint Jacobian at the bottom. And this is then denoted by this last row that we have over here. So we simply break it up over here into the constraint Jacobian and the driver Jacobian. So if we perhaps look at how we defined the joints in our card, we know that the first two joints that we specified are revolute joints. So in this case, I have the first 4 rows denoting the 2 revolute joints. So the first 2 rows for revolute joint acting between bodies 1 and 2. And then these 2 columns pertain to the revolute joint acting between bodies 1 and 3. And you'll notice in this case, I have an X, Y, and a rotational component for each of them. So these are then the 3 coordinates for each body. Since I'm also now working with a revolute joint between 2 bodies, I know it's body 1 and body 2. So I've also created these blocks. So you'll see it's 3 blocks, or 3 columns, 3 columns, 3 columns. So each group of 3 columns indicates the body that I'm working with. Since revolute joint, the first revolute joint acts between bodies 1 and 2, I'm going to group 1 and 2 together, and it's going to have X and Y components. And then I also have X and Y components, so these 2 rows pertaining to the joint or the revolute joint between bodies 1 and 3. Okay, so we're not too worried about the actual values over here, the minus eta 1, P2, these type of things. These you can always go back and check the analysis that we performed for the pendulum rod. I think over here we did look at the Jacobian matrix, so you can actually pull this through to the current version that we're looking at, or the current application example. However, it is important to note how these things are combined with one another. Right, so if I just scroll down over here, then we're back to the 2 revolute joints that we first defined, and then we have the 2 disc joints which follow. So they also impose 2 constraints each. So these will then be the following 4 rows that I have. Once these are defined, so just my regular constraint Jacobians, then I'm just going to append my driver Jacobian at the bottom as well. Okay, so then plotting the torque associated with the prescribed rotation of the rear wheel. If we go and look at that, we can actually go and calculate torque 2, which is equal to Jacobian, and in this case we consider for all time steps, and this will then be row 9, column 6, which I dot and multiply with Lagrange multiplier 9. So I know Lagrange multiplier 9 is going to be my motor driver output, or my Lagrange multiplier pertaining to the relative rotation driver. However, I need to multiply it over here with the Jacobian. So just to double check that, if I check the Jacobian, I can see that indeed I'm working with row 9, so the final row over here, and then it's column 6, so this column over here. And this is because I'm working on body 2, and I'm interested in the rotational torque. So in other words, the torque about the z-axis. So that's why I'm using not the x or the y, but rather the rotation about z component. Okay, so I can then go and perhaps plot this. And if we do that, I'm just going to go back over here. Just say clear all, close all, and we can run DAP again for card B. We still correct the initial conditions. We use a final time of 3 seconds and a reporting time step of 0.1. Right, so then if I run post, then I can say torque 2. So in other words, the torque applied to body 2 is equal to the Jacobian matrix, so that is Jac, all of the time steps, and this is then row 9, column 6. And I dot and multiply this with the Lagrange multiplier for my motor as well. So I'm just going to do that. So the reason why I multiply by this Jacobian entry over here is simply to make sure that I'm working with the correct sign over here as well. If I were perhaps interested in the torque on body 1 and I multiplied now with -1, then the sign would have changed, and I need to accommodate that sign when I do the calculation. In my case, I'm just going to multiply 1 with whatever Lagrange multiplier I get, so the values should in any case just be Lagrange multiplier 9. But to perhaps plot this and illustrate it, I'm just going to say plot T, and then I'm going to do torque as well. Okay, so this is more or less what I get. So my torque starts at 0, it reaches a negative value of 7.3, and then it goes back up to 0 from 2 to 3 seconds. And this is also more or less what I expect, since I have a constant angular velocity after 2 seconds. And if I want to compare this to the results that I got in the PMD textbook, this is the result if I were to just plot Lagrange multiplier 9. So in other words, I disregard this Jacobian, I just plot this part, I indeed get exactly the same. So that is correct. Okay, so then we can also plot the reaction forces associated with the no-slip constraints of the rear and the front wheels. So to do this, remember that the no-slip constraint refers to the x direction. So to ensure that I have sufficient friction between the contact surfaces to not allow for any sliding or slippage to occur. So if I quickly go back to my Jacobian over here, and I consider, I believe it was on body 2 and body 3, then I want to consider in the x direction, so something tells me that I'm going to have to multiply with Jacobian row 1, 2, 3, 4, 5, 6, and then it will be this component over here, so that will be 4. So Jacobian 6, 4. And if I just go down, I can see that that is indeed the case, and I multiply that then with Lagrange multiplier 6. So I always make sure that if I multiply with row 9, I'm going to multiply with row 9 in my Lagrange multiplier as well. In this case, I have Jacobian row 6, which I multiply by Lagrange multiplier 6. So that's also correct. And then if I want to check no slip 3, then I need to work with body 3. So in this block that I have over here, I'm once again interested in the x component. So I'm going for the second constraint that's specified for the disk. And I know this is row 9, so this will be row 8. So, and this is 3, 6, 7. So it's Jacobian 8, 7 multiplied by Lagrange multiplier 8. And if I just double check that, I can see that that is indeed the case. So I'm just going to plot this as well. And what I'm going to do is first define no slip 2, which is then equal to Jacobian for all of the time steps. And I think we said it's 6, 4 dot, and I multiply with Lagrange multiplier 6. And then I can also do no slip 3, which is equal to the Jacobian, all of the time steps. This will be row 8, column 7, dot multiplied by Lagrange multiplier, and this will then be column 8 as well. Okay, so then I'm just going to say plot T no slip 2. Then I can say hold on, just to make sure that it doesn't plot the next plot over this one. So I want to show both of them on the same plot. And I'm perhaps just going to use, let's say, a blue line for this one. And then I'm just going to say plot T no slip 3, and this we can use a blue dashed line for that one. And then I'm just going to say hold off. Okay, and this is then the relationship that I get over here. If I go and compare this to what we get from the PMD textbook, we can see that this is indeed the same. And I could actually use just Lagrange multiplier 6 and Lagrange multiplier 8, because if I go back to the Jacobian matrix, I can see that they are both only multiplied by 1. So I don't need that Jac 8-7, Jac 6-4 in front of the actual calculation of the reaction forces. Okay, so we note that the reaction force on the rear wheel is positive since this is the driver wheel, but for the driven wheel at the front, it is negative. Okay, so this is basically what this graph tells us over here. And that is why we also wanted to compare no slip 2 to no slip 3. Okay, and I believe this also then wraps up what we wanted to look at for exercise 8.8 and then also for part B. So just to give a quick review of the two lecture parts that we now considered for lecture 6, the first part focused on part A, where we just use a simple type A function. We working with a constant angular velocity over there, so we do need to perform some initial condition correction. Whereas with part B, we can actually define a sort of a raise or a ramp up of our angular velocity from 0 up to the -2 pi radians per second. And we could then relate the mechanics or the dynamics of that to calculate the torques. And we also saw how we can utilize the Jacobian matrix to double check our sign convention for the actual plots that we generate. Okay, so in the next lecture, we're going to consider a few other examples of the cart as well, so additional extensions of that. But for lecture 6, this is where we're going to end.